Ken Olson, a renowned American engineer and the founder of Digital Equipment Corporations, once said, "Software comes from heaven when you have a good hardware." In the world of digital systems, good hardware starts with good design languages like Verilog HDL. Evolution of hardware description languages through the ages.
Early digital circuits were built using vacuum tubes and transistors. As these technologies advanced, integrated circuits were developed, allowing multiple logic gates to be placed on a single chip. The first integrated circuits were small-scale integration chips, containing only a few gates. As technology progressed, medium-scale integration chips followed, allowing hundreds of gates on a single chip. As complexity increased further, large-scale integration emerged, allowing thousands of gates to fit on a single chip. This increased complexity meant designs had become too complex to be verified using traditional methods like breadboarding. To meet this challenge, engineers turned to computer-aided techniques, enabling the simulation of digital circuits and easing the verification process. This growing complexity prompted the need for automation in design processes. This gave rise to electronic design automation, which made use of computer-aided techniques to design and simulate digital circuits before they were physically created. By the time very large-scale integration arrived, circuits with over hundreds of thousands transistors were being designed, marking the beginning of a new era of automation. By the 1950s and 60s, as integrated circuits became increasingly complex, the need for automated design tools became more pressing. In the 1970s, a new idea came up. Instead of drawing circuits, engineers could describe them using text, similar to writing software. This led to the development of hardware description languages. Early experiments in 1970s introduced the notion of describing hardware with text, but wide adoption by the design community did not start until after 1985. A significant milestone came with the development of ISPS, which stands for Instruction Set Processor Specification. ISPS was well suited to describe relations between the input and output of the design. ISPS allowed to describe the instruction set of processors, setting the foundation of future HDLs. One of the first hardware description languages to gain widespread commercial use was PAL assembler, developed by Monolithic Memories. PAL assembler was designed to specify logic equations for programmable array logic devices. Although it has limited capabilities and resembled assembly language, it introduced the concept of using a text-based language to describe hardware logic. This idea soon led to the competing languages like CUPL and ABEL, which added more powerful constructs like if-else and case statements. By the mid-1980s, two significant developments in the world of hardware description languages would change the landscape of digital design forever: the rise of VHDL and Verilog. VHDL stands for VHSIC Hardware Description Language, where VHSIC stands for Very High Speed Integrated Circuit. VHDL was developed by the US Department of Defense. At the time, there were several different hardware description languages in use, but each had its own syntax and semantics, which made it difficult to exchange design information between different design tools and environments. The Department of Defense recognized the need for a standard hardware description language that could be used across different design tools and environments, and VHDL was developed to meet this need. It described the behavior and structure of electronic systems. VHDL was powerful, but its formality and complexity turned some designers away. Meanwhile, in Silicon Valley, another HDL was quietly rising to prominence: Verilog. Developed by Phil Morby at Gateway Design Automation in 1984. Its syntax was influenced by the popular C programming language, making it easier for software engineers to adopt. Gateway was later acquired by Cadence Design Systems, which places the language in the public domain in 1990. The Open Verilog International was then formed to promote the Verilog HDL language. In 1995, Verilog was made an IEEE standard HDL and is described in the Verilog Hardware Description Language Reference Manual. Now Verilog is widely used for design and verification of digital and mixed signal systems, including both ASICs and FPGAs.
It supports a range of level of abstraction from structural to behavioral and is used for both simulation-based design and synthesis-based design. Synthesis in the context of hardware description languages is the process of converting high-level abstract descriptions of a digital system into a gate-level netlist that consists of basic hardware elements such as logic gates and flip-flops. This netlist is then used to create the actual physical hardware. The language is used to describe digital circuits hierarchically, starting with the most basic elements such as logic gates and flip-flops and building up to more complex functional blocks and systems. It also supports a range of modeling techniques including gate level, RTL level, behavior level modelings. Basic modeling structures. A module in Verilog is the fundamental building block for hardware design. It typically contains port declarations, data type declarations, the circuit functionality, and time specifications. These components together define how a hardware circuit behaves. Each section of the basic modeling structure is further explained using an example. The general structure of a Verilog code is a module description, which serves as the basic building block by declaring the input and output signals and specifying the internal operation of the module. In the light of given example, the first step to describing a module is to marking the beginning and end of the module description with module and end module statements. We then give the module a name. This name is the identifier of the module. Identifiers are the names given to the object so that they can be referred in the design. Identifiers are made up of alphanumeric characters, underscore, or the dollar sign. Identifiers are case sensitive and they start with alphanumeric characters or an underscore. Next we describe how the module connects to the outside world using what called ports. Ports indicate the direction of information, whether the information is flowing into the port or out of the port. Input port signals are of the keyword input, output port signals are of the keyword output, and bidirectional signals are of the keyword in-out. Keywords are special identifiers reserved to define the language constructs. Keywords are lowercase. In our example module has 3 ports and each of these need to be given a name and then describe whether these are input ports or output ports. Ports are listed in a way that first listed output ports then the input ports. Next we will describe our module by specifying the submodules used within the parent module. Verilog provides building primitives for logic gates such as AND, OR, and NOT. However, we instantiate these primitives in the same way as we would any other modules. Module instantiation. A module serves as a template to create actual objects. When a module is called, Verilog generates a unique instance based on this template. Each object has its own name, variable, parameter, and I/O interface. The process of creating these objects from a module template is known as instantiation, and the resulting objects are referred to as instances. Complex systems can be designed by combining subsystems. So we will design the simple subsystems and then we will call them as a function in the top module. There are 2 methods of module instantiation in Verilog. First one is port connection by ordered list. Another one is port connection by name. Port connection by ordered list. We use ordered list inside the parent module to instantiate the lower modules. Here we must know the exact order of ports in the lower module to make the right connections. This approach can be very inconvenient if we have large number of ports or sometimes if we add another port in the parent module, even though we used this method in our example. Port connection by name. It is slightly a better way. Here we don't have to remember the order, but we will just remember or we will look at the name of the port, and this way is to link by calling the names of each port one by one. In this approach we use dot symbol to indicate the port mapping and also use brackets. The submodule port is written after the dot and then inside the bracket we write the lower module. We can mention the port in any order without changing the topology. Coming back, after we instantiate the OR gate in our module, we see that its input connects to the input ports of the module X and Y. We write X and Y in the input for the definition of OR gate, indicating that the OR gate input are connected by wires to our module inputs. But the OR gate output connects directly to the AND gate. To handle this, we need to declare a wire for our module. Wire is a data object that represents an electrical connection and is used for passing values between components. For this module, we need to declare two wires, such as OR wire and NOT wire. The order of module instantiation doesn't matter, as it only describes the connections, so we can change the order without changing the topology. Different types of modeling. Verilog is a hardware description language used to simulate complex digital or logic circuits. Logic circuits can be modeled in different ways, using logic equations as an interconnection of various subcircuits, using the behavior of the system under consideration, using MOS transistors, or even as a mixture of any two or more of the above. If we model a circuit by using basic logic equations, then the style of modeling is called data flow of modeling. If the system is represented as an interconnection of transistors, then the style is switch level modeling. If the system under consideration is represented as interconnection of subcircuits, then the style is called structural modeling. If we model a system by considering the behavior, then the style is behavioral modeling. If the system is modeled as a mixture of above styles, then it is called mixed modeling. First, we are going to discuss data flow of modeling. In this slide, I have shown the verilog code for an 8x1 multiplexer along with its block diagram. The verilog code for the multiplexer in the previous slide is modeled using the basic logical output equation of the 8x1 multiplexer. This style of modeling is called data flow modeling. The first line defines the name of the module as mux 8x1. D7 down to 0 represents the 8 inputs, S2 down to 0 represents the 3 select lines, and Y is defined as the output port. A ternary operator is used to assign a value to the output port Y based on the value of the select lines. The values 3B000, 3B001, etc. are binary numbers that represent the select lines in 3-bit wide binary form. Depending on the value of select line, one of the data inputs D0 to D7 is selected. The statement end module indicates the end of the module. We know that for an 8x1 multiplexer, output Y equal to I0 if S2 equal to 0, S1 equal to 0, S0 equal to 0, or Y equal to I7 if S2 equal to 1, S1 equal to 1, S0 equal to 1. If we are modeling a circuit based on its behavior, then that type of modeling is called behavioral modeling. The behavior of a design is described using procedural constructs like initial statement and always statement. Initial statement executes only once, whether always statement executes always in a loop. Only a register data type can be assigned a value in either of these statements. A register retains its value until a new value is assigned. Now let us consider structural modeling. In the style of model, the circuit under consideration is represented as an interconnection of different subcircuits. For example, let us consider a 8x1 multiplexer. Here a 8x1 multiplexer is realized using two 4x1 multiplexer and one 2x1 multiplexer. In this modeling, device under consideration is modeled as an interconnection of subcircuits. Structural modeling can be done using instantiation. Various instances of subcircuits are interconnected by nets. Basic logic gates and transistors can be used as a subcircuits or instances. Now mixed style of modeling. Here to implement an 8x1 multiplexer, we have used two 4x1 multiplexers, one inverter and one OR gate. Here we are using structural modeling to instantiate two 4x1 multiplexers, and we connecting the output of these two multiplexers to the input of an OR gate. There is data flow modeling also. So this modeling contains two different styles of modeling. This type of modeling is called mixed style of modeling. Combination of data flow structural, data flow behavioral, structural behavioral, switch level structural, all are examples of mixed style of modeling. Next style of modeling is switch level modeling. Here in the diagram, an 8:1 multiplexer is represented as an interconnection of various NMOS transistors. The circuit under consideration can be modeled as interconnection of MOS transistors. Then the style of modeling is switch level modeling. In CMOS logic circuits, there is PMOS network and NMOS network to realize the required functionality. Logic circuits which are implemented using transmission gates are also modeled in this style of modeling. Data types. Verilog has two main groups of data types, the variable data types and the net data types. These two groups differ in the way that they are assigned and hold values. Net data types. The net data types can represent physical connections between structural entities such as gates. Generally, it does not store values. Instead, its value is determined by the values of its drivers, such as a continuous assignment or a gate. Variable data type. The variable data type is an abstraction of a data storage element. A variable shall store a value from one assignment to the next. An assignment statement in a procedure acts as a trigger that changes the value in the data storage element. Common net data types. First one is wire, the most basic net data type used to connect components. It cannot hold a value but reflects the value driven on it. Another one is tri, represents a tri-state connection, allowing for three states, high, low and high impedance. Next one is WAND, stands for wired and, where the result is true only if all the drivers are true. Next WOR, stands for wired or, where the result is true if at least one driver is true. Common variable data types. First one is reg. Despite its name, it does not imply physical registers, but denotes a variable that can hold a value in procedural contexts. It can be useful for modeling state elements or temporary storage. Next one is integer, a whole number, typically useful for counting or indexing. Another one is real, represents floating point numbers, useful for modeling analog behaviors. Next, time, specifically used for time-related operations. Real time represents a floating point value with a time unit, useful for precise timing simulations. Parameter. In Verilog HDL, constants can be defined within a module using the parameter keyword. A parameter can be used as a variable, but its value can be overridden for each module instances at compile time. When a constant is used repeatedly throughout a design, it can be replaced with a parameter, allowing the value to be defined in one central location. If the constant value needs to be changed in the future, only the parameter's value needs to be updated, and the change will be reflected across the entire design. There are three ways to declare a parameter. We can declare a single parameter using the parameter keyword as follows. Parameter pair1 equal value 1. In this case, pair1 is a parameter and its value is value 1. To declare multiple parameters, we can use a single parameter keyword as shown. Parameter pair1 equal value 1, pair2 equal value 2. Here pair1 is the first parameter with a value of value 1 and pair2 is the second parameter with a value of value 2. We can declare as many parameters as needed by separating them with commas. If the parameter needs to be in bit format, we can declare it accordingly. Parameter range pair1 equal value 1. For example, if the parameter is a 3-bit value, then pair1 is a parameter with a 3-bit value ranging from 3b000 to 3b111 and its type is a parameter with a value of value 1. Another way to define constants is by using local parameter. The syntax is local parameter constant name equal constant value. A local parameter is similar to a parameter, but its value cannot be changed externally. It is useful for defining constants that should not be modified. While parameters are typically used to customize module instances, such as specifying delays or the width of variables, local parameter ensures constant remaining fixed and unaffected by external overrides.